Hey, good afternoon, everybody.
Afternoon.
Good morning.
Good morning. Yeah, it's morning to me, actually. All right. Hope everybody's doing well. Hope you've had a good couple of weeks since spring quarter ended. It's definitely gone by quickly, but
A little too fast, actually.
let's see. All right, so welcome to Engineering 270. This is the sequel to Engineering 250. It's primarily a course on two things: microprocessors and assembly language programming, but also kind of more generally computer architecture. Um, and some of you have completed the 200 level computer science sequence, 224, 23 if you're computer science track, and some of you have not taken that yet. In general, I find that people who have already done the CS sequence find that this course is relatively straightforward and really explains a lot of the mysteries of those 200 level CS courses. Um, People who take this course first find this perhaps more challenging or challenging in different ways, but then when they get to the 200 level CS courses, they find that what they learn in there makes this course make a lot of sense, and that what they learn in 270 helps them with those courses. So it's really kind of a foundational subject. Even if you're never going to write assembly language or work with a microprocessor directly, it really kind of helps with the understanding of computer science and engineering in general. Um, if you're strict double E, if you're not doing any computer science, there's still a good chance that the engineering you're doing will be interacting with microprocessors because they're just such a part of most systems that we build today. So hopefully you find this course useful down the road, but hopefully you find it interesting and actually pretty fun, despite being a required course and having homework and stuff like that. Um, it's actually a pretty fun subject, and most people come away enjoying it. So let's see. So I do record my lectures. I'll post these on YouTube. There's a link on Canvas to these. Um, I do not put any student specific information on the screen. What I'm recording is basically everything that you see here. Whether it's coming live. I'm not showing my screen. Hold on a second then. I have, yeah, so things crash. So I'll make my disclaimer right now. Every time that I do this, start a new course, the degree to which Zoom is working kind of varies. And we'll see if we can get it to work well. All right, there we go. So what I'm recording is basically what I'm sharing, what you see up here, whether it's my document camera or using the software tool we're going to be using or whatever like that. So that will be posted on YouTube and available after class. So you don't need to spend your class time writing down every single thing that you see, right? It's recorded. Um, your best option though for class time is to try to spend class time to understand the material, right? Think about the concepts we're going over and see what you understand, what you don't understand, ask questions about what you don't understand, and really try to learn while you're in class here. And then, if you need to go back and see what was that sample code that was written, right, you can go back to the lecture videos and catch those. But the more you can kind of engage with the subject and the course while it's happening, the better the better you're going to understand and retain this material. All right, so we have some administrative stuff to go through today, just because I need to say the stuff up front and make sure everybody's heard it, and then we'll jump into talking about more details about what we mean by a course on microprocessors and assembly language. And before class is over today, class ends at 2. Before then, we'll have gone through the first lab so that you can begin working on lab 1 today. But let me start off by going through the syllabus and things like that. All right, so second course in 2-digit sequence, we've talked about that. Class hours, so we meet Tuesdays and Thursdays 12 to 2, okay? If you're here, you've probably already figured this out, but just to make sure that everybody's clear on this, this is not an online course in the pure sense. It's not a do-at-your-own pace course, okay? It's basically a face-to-face class, traditional class, except that instead of being face-to-face, we're working through Zoom. But you're expected to be here Tuesday, Thursdays, 12 to 2. Those are the only times that the course is happening. So it's not a kind of like, you know, watch the material at your own pace kind of thing. The textbook is a free download. You can link to it through here. We'll cover a lot of the material that's in the textbook. There's some stuff we'll cover that's not in there. There's definitely stuff in the text that we won't get to this quarter. But we'll more or less follow the general flow of the textbook. There's a data sheet for the processor we're using. So we're working with a particular microcontroller called a PIC 18F1220. And just like every chip that we use in Engineering 250, there's a data sheet for this chip. It's 300 some pages long. Okay, so I strongly recommend downloading that and having it available. And we'll use a lot of information from that data sheet, so that's almost like a second textbook for the course. C programming language can be useful. I mean, it's a great text to have anyway if you can get a copy of it. We're not doing a lot of C in here per se, but we will talk somewhat about how C and assembly language relate to each other, and looking at that connection when you compile a program and see what does it turn into, and we'll do some of that by hand. And computer architecture, Hennessy-Patterson, that's sort of the gold standard for computer architecture, but not a required text for this course. You can go through the course outcomes on your own. These are the things basically that we're certifying. If you pass this course with a C or better, we're saying that you've achieved these required outcomes, and this gets you equivalency for classes when you transfer to your university and try to take 3rd and 4th year courses. Very tentative course outline. This will change depending on what pace we go and which way the sun swings. But rough tentative outline here, where these chapters are chapters from the textbook, so 2.1, 3.1, and so on. All right, grading. So straightforward grading calculation. So 15% for homework. You'll have 1 homework assignment a week, generally due on Tuesday. Attendance 15%, so we have 15 days of lecture, and then the last day is the final exam, so it's basically 1 point per day of attendance. 15% for labs. Labs are given roughly once a week and generally due on Tuesdays. Comprehensive midterm at the end of week 4, that's the halfway mark, that's a quarter of your final grade, and then the final exam is 30%, and that's the last day of the class. Work needs to be done individually, right? You can talk with classmates to try to understand concepts. You can ask questions to each other, or of course to me, or in class, or in lab hours about, you know, problems, things you're stuck on, and so on and so forth. But whatever you turn in with your name on the top of the assignment, it's got to be your own work, right? And there's a line between collaboration and what would be considered academic dishonesty. So I don't want you to, you know, shut yourself off from other students during this course, but make sure that what you're turning in is your work that you've done and that you understand. You also need to complete all labs before the final exam in order to pass the course. If you're missing a lab and you've got, an 85%, it's going to be an F unless you turn in that missing lab. So make sure all of your labs are turned in before the final exam, that last day of the class. So it's a remote class. Everybody who's here obviously found the Zoom site. And again, it's not, sort of classic online class. It's Tuesdays, Thursdays, 12 to 2. Attendance. Okay, so attendance is required for every class, and we'll talk about how I'm planning to take attendance in a few minutes. It's listed in Canvas, but what I want to mention here is that if there's a situation where attending every class is going to be a problem for you, for example, if you work, right, Tuesdays, or maybe every day of the week during class time, or if you're taking care of a family member or you're homeschooling, and you may not be able to be sitting at your computer every minute between 12 and 2, let me know, okay? Let me know this week. And we can talk about your situation and see if there's some kind of flexible attendance that would be appropriate here. But you got to do that this week, okay? By the 9th of July. Let me know about this and we'll talk about it. Barring that, right, I'm going to expect everybody to be here for the full 2 hours, 2 days a week. Academic honesty and plagiarism, I don't want to talk too much about this, but basically all your work has to be your own work. If you copy someone else's work, if you download work, if you have someone else write part of your code or come up with your circuit for you, if you take someone else's work and then modify it to turn it into your own, all of these things are considered academic dishonesty. And if I see this happening, right, it will be an automatic 0 on that assignment and a warning. If it happens a second time, you're out of the course. Okay, it's an F for the course and possibly further action involving the honor board at Clark College. If you have any doubts about this, just ask me. Okay, the lines can be a little fuzzy, but if you're clearly in the wrong side of that line, it's usually pretty obvious, right? It can get a little blurry sometimes, but if you're doing a lot of looking around online for things, if you're Googling parts of a question from an assignment and then taking the answer and changing variable names, you're probably pretty far on the wrong side of that line. So ask me if you have any questions about this. But I'm taking this increasingly seriously going forward because in the past year, I've just been seeing more and more of this happening. And it's a really bad trap to fall into, particularly since by the time you're transferring to your university, things are going to be back to in-person. And if you're getting into these habits of using outside resources that you're not supposed to, then it's going to kind of all fall apart when you're in a classroom setting. Late papers. Deadlines are listed on Canvas. Like I say, generally things are due on Tuesdays. Everything's got to be turned in by the deadline. All right, and the deadline is according to Canvas. So if you turn it in at 12:01 and your computer says it's 12 o'clock and Canvas says it's late, it's a 0. Okay? The exception is you get 3 slip days. All right, so if something happens, if you turn it in a few minutes late or you can't turn it in until the next day, right, you can take a slip day. And you get 3 of these allowed, and you can use these on labs, you can use these on homeworks. You can't use them for exams, though. So if an assignment is due Tuesday at 12 and you turn it in Tuesday evening, right, that's 1 slip day. I'll accept that. I'll take it as having been turned in on time. So I'll still grade it. You get a grade for it. But you've used 1 slip day. If you turn it in 2 days late, you use 2 slip days. If you turn in another assignment 1 day late, that would be your 3rd slip day. After that, if you turn it in late, it's a 0. All right, so that's intended to be very straightforward, but if there's questions about that, let me know. All right. Missing the midterm or the final, though, is going to be a 0 unless there's some very severe documentable reason why you missed it. If you forgot about it, it's going to be a 0. Okay? So please, please, please don't miss your exams. All right? Support services, if you feel like some kind of accommodation would help you be more successful in this course, extended testing time, having a note taker, if we were in a physical classroom, testing in a low distraction environment, having a reserved seat near the front of the class, anything like that, right? Talk to me or talk to the Disability Support Services Office, DSS. There's their webpage, phone number. You can find Zoom information on their website, and accommodations can be made, right? And there's a wide range of accommodations that are available depending on what your situation is. So please take advantage of that. Non-discrimination policy, hopefully everybody is familiar with this, and I don't need to read through this word for word. I usually do, but at this point everybody should have been here for at least the past 3 quarters at this point. But make sure if you've never read through this, read through this, and this is another thing we take very seriously. Class cancellation, if it snows, we'll post something on clark.edu, and then ECS course policies, you can click through to that. So any questions on that sort of administrative side of things? All right, so let's talk about attendance. So as I said, there's 15 class meetings before the final exam. And since attendance counts 15% of your final grade, basically each class gets you 1 point, or each missed class docks you 1 point. So if your homeworks, labs, exams bring you out to an 80% for the course, but you missed 5 classes, you're down to a 75. If you miss 6 classes, you're down to a 74. If you miss 1 class, it's a 79. If you come to every class, you'd get your 80%. So it's really 1 point per class, which is pretty significant if you were to habitually, just come to every other class, you're going to drop a letter grade or more, just based on attendance. All right, so how are we going to do attendance? Basically, during class at different times, I'll say, okay, I'm taking attendance now. And I will give you a minute to send me a direct message through chat. And your direct message should be your Canvas name, okay, so first name, last name, and then a dash, and then the word here. All right. And I'm going to ask you to do it in exactly that format. First name, space, last name, middle name in the middle if you like, and then just a dash, and then uppercase H-E-R-E, and nothing else. Don't say I'm here, don't say here with an exclamation mark, because you're going to process this using some automated tools to scrape attendance information. So let's go ahead and do that just as kind of a baseline test. Go ahead, and if you are here, send me a direct message through chat with your Canvas name, dash, and the word here. I'll give you a minute to do that. Awesome. People are here.
Private message, correct?
Say again?
Private message.
Yeah.
Okay, thank you.
Yep, you're welcome. All right, perfect. Looks like everybody is here. So we'll do that a few times during lecture. So if you have to step away from your computer, you've got to take the dog out or get a glass of water or something like that, right? Sorry, say again? I think your microphone's on. All right, so if you have to step away from your computer, just go ahead and send me a private message with your Canvas name, dash, and AFK away from keyboard. Just to let me know that if I happen to take attendance right then and you don't say that you're here, it's because you're not at your keyboard. And then when you come back, just send me your name and say back. So this is like, if we were in a physical classroom and you had to get up to leave for a minute, I'd know that you're walking out, so that if I took attendance right then, I wouldn't mark you as being absent. All right, does that make sense to everybody?
Yep.
All right, cool. All right, so next thing, for lab hours, I'm going to be in a different Zoom room. So lab, I'll be available immediately after class for 2 hours, both Tuesday and Thursday. So from 2 o'clock to 4 o'clock. But I'm in my regular office hours, so the Zoom link is over here. And this room has a waiting room in it. So if you connect to it and I don't start talking to you right away, I'm probably in a meeting with somebody else. So just hang out and I'll take people in order. And usually if there's a lot of people, I'll send a note and, just let you know that I'm still here and I'll get to you when I can. But this is a good time to come in and, talk about lab questions or homework questions, to screen share if you're having trouble with the software. If you have, concerns about the course or anything like that, that's a really good time to catch me. This is mostly reserved just for this class, but I'm also marking an hour of this on Thursday for general office hours. So there might be someone, from outside coming in for advising or something. But if that starts taking away time from this, I'll dedicate this time completely to Engineering 270. So definitely take advantage of that. And again, if sort of habitually that's not going to work for you, if there's no way that you can come in any time between 2 and 4 o'clock on Tuesday or Thursday, let me know this week, right? Because I'm going to expect if people have questions, that's when we're going to talk about it, is either in lab hours or during class. Okay, I'm not going to be giving help over email. I'm not going to look at your code on email and debug it for you. It's going to have to happen when we can screen share and we can work back and forth on something. So if those hours are a definite problem for you, let me know.
If we are, say it's like Friday, we just have a simple question, not like anything complex, emailing an action question, or is it only Tuesday, Thursday?
You can always send me an email, and if it's something that is easy to deal with through email, I'll go ahead and respond to it. But I'm trying to avoid emails on Saturday night saying I don't understand microprocessors. Can you explain them to me? Right? That's an office hour thing. So, but yeah, you can always email me. In worst case, I'll say let's talk about this on Tuesday.
Okay, thank you.
All right, you're welcome. All right, homework. All of your homework questions come from one big set of questions that you can click through on Canvas. So I've just written up 100 some questions to pull from. And for each week, I'll indicate which questions you should be working on. So your first homework is due July 13th, so that's a week from today. And I want you to write up questions 1 through 9 and 11 through 17. And we'll be working through the material for that today and on Thursday. But hopefully we'll get through most of that today. So if you've had me for 250, you've already seen this. If not, short guide on how I would like you to write up your homework. And I don't think I need to read this to you line for line, but I'll give you the synopsis of this, then I'll ask you to read through this on your own line through line. Basically, my goal in this guide to writing up homework, I want your homework to be written in a way that I can follow what you've done. Okay? You need to show your work where appropriate for your answers to homework questions. If there's a calculation to do, I've got to see the calculation. If you're writing code, right, then there's no work to show, but I want to see your code. But I need to be able to look at your homework and understand what you've done and understand what your answer is. So I want your homework organized from top to bottom, one page, next page, next page, next page, right? Don't give me little mazes to follow with arrows that come back around, to the top of the page and then put, question 7 before question 3 and so on. Just organize it in a way so that I can look through it and I can understand what you've done. In particular, so I can try to give you partial credit if you didn't get the correct answer, but you were on the right track. So work neatly, I recommend a good sharp number 2 pencil, a good eraser. Do your homework first and then write it up in a way that you want to turn it in, which is also good practice for learning the concepts better and so on and so forth. Your uploads are done as a PDF file, so you definitely want to get good at writing on paper and turning it into a PDF, because this is also how you're going to do your exams. And you don't want that to be something that takes a chunk of time. So you know, nice clean screenshot if you don't have a scanner. You know, camera images work great. If you're really comfortable writing things up electronically, you can do that, that's fine. But I don't want that to be something that takes time away from you know, learning the material and working with the material. So you want to figure that out, and homework's a good opportunity to do that. So your homework gets turned in as a PDF, and you know, just some basic stuff. I'd like to see your name at the top of the assignment, along with the class, the homework number, the date, and number your pages. Again, just so I don't have to hunt around. Use your full name. We've got people with the same first name. We've got people with similar initials, right? Always use your full name on turning stuff in. And if there's a single answer at the end of your problem solution, circle it or draw a box around it or something, so that I can quickly look and see what the answer is you came up with, and then scan the work to see how you got there. So I'm not going to be, like, you know, super dogmatic about this, but like I say, the goal is to be able to follow your work and understand how you got the answer. All right, and labs are a big part of the course. Labs are where you're going to do most of your actual learning, followed by homework. And the main way that I have for assessing what you've done in your labs is your lab reports. So again, I'm not going to read this to you verbatim, but you're going to spend, you know, a few hours doing a lab. You're going to write lots of code and find bugs and take care of them and all this kind of stuff. You're going to put in a lot of work. I don't get to see that, though, right? What I get to see is your report that documents what you did in your lab. That's what your grade is based on. So you need your lab report to be high quality, well written, and reflect everything that you did in the process of doing the lab. So again, it's uploaded as a PDF. It's got to be typed or computer printed. You can neatly draw figures if you like, but everything else has to be, you know, typed, well organized, and so on and so forth. Any code that you write in your lab has got to include a detailed flow chart. Now, the lab itself says you can include pseudocode. I'm insisting on a flow chart. We're going to talk about flow charting today, or on Thursday, but I want to see pseudocode in the form of a flow chart for any program that you write for your lab. Everything should be in your own words. If you copy anything from the lab assignment, from the textbook, you've got to reference it, right? And all you need is a little note on there saying, you know, taken from Intro to Computer Design, page 75, or wherever you got it from, taken from, you know, Lab Assignment 2, Engineering 270. But anything in your lab report that is not cited as belonging to something else is taken as being yours. And if it's not yours, that's academic dishonesty. And I'm not going to kick you out of the course for that, right? But other teachers will. So we want to use this as practice to make sure that we're citing things properly. And organization, so a cover page. If you've done 250, you've probably gotten the same thing in other classes. This is exactly the same as my class. Cover page with the name of the course, your full name, date, lab number, and so on. And then beginning on the next page, I want an introduction. Okay, it can be one sentence if you like, but something that describes this lab, you know, overall. And then start with experiment 1. And for each experiment, basically describe what it is that you're doing, what the procedure is that you're following, and then tell me what happened when you did this. Put down your observations, right? So you're doing labs to, you know, test something. I believe that if I do this and then I type these things in, this will happen on these LEDs, right? So document what you're doing, basically, right? The goal is somebody should be able to pick up your lab report and reproduce your work from it. Okay, and that's really kind of the gold standard that I use in assessing your lab report. If I were to pick this up, knowing nothing else except what's in this lab report, could I reproduce your work? Okay, so you want enough information in there to let somebody else do everything that you did. In addition to, you know, answering questions that are asked in the lab and so on and so forth. And then at the end, I'd like to see conclusions and lessons learned. So sort of summarize, you know, what's the takeaway of all of this work for you? What did you learn here? And then everyone's favorite section, a section called New Experiment. And for New Experiment, I want you to come up with a new experiment that somehow, you know, continues or extends the ideas of the lab. And spend a lot of time coming up with this. Because then you're going to actually write up the experiment in detail, and then you're going to perform the experiment. Okay, so it's got to look just like one of the other experiments you've done, but you know, something that you come up with on your own, and then actually do the experiment. This is going to be really tricky with Lab 1 because Lab 1 we don't really know a whole lot yet, but we'll still have some options for new experiments there. All right, so you can read through that in detail, but that's basically the highlight. If you have not had me for Engineering 250, I will be more forgiving on your first lab report, and I'll give you lots of feedback to let you know, yeah, this is exactly what I was looking for. This was pretty good, but I'd like to see more of this, and so on and so forth. So we'll modulate around that and get where we're going. All right, so here's a link to my YouTube channel that has we'll have the lecture videos for this course. This is actually for my entire 2020-2021 computer science and engineering sequence. You can also click through to a list of topics, and this gets added to at the bottom. So if you go down to the bottom, you'll see Engineering 270. And so on and so forth. But this basically shows you, the different videos that are out there and the timestamps for them. And if you go to YouTube on one of these videos, the timestamps are bookmarked in the description, so you can move around pretty quickly. So that can be useful if you're trying to go back and, what the heck did he say about such and such? You can find it in there. All right, I think that's it for administrative stuff. Questions on any of that? All right, cool. So let's talk about computers. So you've done, CSE 120, we do a little program in there, or Engineering 120. Engineering 250, digital logic, so we've played around with, pretty simple circuits involving gates, memories, small state machines, things like that. You should have done CSE 121 at this point, so Intro to Programming in C. So you've got some knowledge of computer programming, right? And generally when we program in C or Python or Bash or Java or something like that, we're working in what's called a high-level language. Okay, high level in the sense that it's relatively painless to write even a kind of sophisticated statement. Like if you wanted to find the root of an equation, right? We could say something like x equals negative b plus square root of b times b minus 4 times a times c, and we could throw in some extra parentheses. We could divide by 2a, and we could say, if a is not equal to 0, x1 equals this, and x2 equals, the whole thing minus the square root, and, and this is basically, we learned the quadratic equation in school, and this is, pretty close to what we learned. I had to say SQRT instead of the official square root symbol, right? But going from a quadratic equation that we learn in school to a statement like this, pretty straightforward. And we know if a is 0, this will blow up, so we don't want to do this if a is 0. So, we say if a is not equal to 0. Well, if you're comfortable with programming, writing something like this is not terribly complex, right? It's certainly, once you've done it a few times, it's pretty straightforward. Okay, this is a high-level language. It's a language that is readable and writable by humans without too much effort. But this means nothing to the actual hardware inside a computer. So think back to 250, right? Think about building a circuit for a traffic light controller. And we spent, almost 10 weeks just doing that, making something that would control 3 lanes of traffic, red, green, and yellow. And how much hardware did it take, and how much work did it take to figure out how to set up that hardware, and how much did it take to debug, right? For something that in the grand scheme is a relatively simple function, right? 3 lanes, 3 lights, priorities, highest priority gets green. When priority changes, green turns yellow, and then red, and then highest priority turns green. That's it, And it was a real pain to build, right? So imagine trying to build a piece of hardware out of AND gates, OR gates, flip-flops that can understand something like this. That could look at the ASCII codes for I and F and parentheses and A exclamation mark equals 0 close paren, and somehow, based on the value stored in a flip-flop register called A, decide whether or not to do these things, right? So performing complex functions directly in hardware, really difficult, really fun, but really difficult. So we, have computers, and computers don't understand this stuff. They understand very basic things. Things like, if there's a car on west, then set west green equal to 1, right? So think in terms of, the instructions that you gave to your circuit in terms of AND gates and inverters and flip-flops. That's the level of things that we can build hardware to do. Not something that can, take an expression like this and calculate what the value of x1 should be. So computers work in a low-level language called machine code. That's sort of the native language that CPUs speak. And what does machine code look like? It's a bunch of ones and zeros. And most of us can't make heads or tails out of machine code. It just looks like a bunch of ones and zeros. But the hardware inside a computer just chows this stuff up. It knows exactly what this means, and it can respond to it in a very precise way very quickly. And so the challenge is, as humans, we want to write things that look like this, but our computers want things that look like that. And so we need to take, if A is not equal to 0, x1 equals blah, 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 and turn it into the ones and zeros that will cause a computer to perform these actions using, the hardware that makes up that computer, that CPU. And so there's this picture you'll see a lot of. And we'll just pick on C because C is an easy target. So this is our high-level language. This is our source program in a file maybe called main.c, which has stuff like this in it. And we have to compile this. And ultimately we need to get down to machine code, which is, if we were on Windows, maybe main.exe, or, a.out if we're on Unix. And this just looks like a bunch of binary data. And most languages that are compiled like C, we don't compile directly down to ones and zeros. We compile down to something called assembly language. This is where we're going to spend most of the next 8 weeks. which might be something like main.asm. It's actually .s, but for us it's going to be main.asm. And then this goes through something called an assembler, and it goes into some intermediate state, and then it goes through something called a loader or a linker, and that's how we get down to the ones and zeros the CPU reads. So there's all these levels of translation taking place, and we're going to mainly work with this. We're going to learn to write assembly language. And the reason we compile from C or some other language into assembly language is that assembly language is really close to these ones and zeros. But it's a human readable version of these ones and zeros. It's not as readable as this, but if you understand the assembly language, it's still pretty easy to look at and figure out what's going on, especially if it's well written and if it's well documented, commented. So we're going to mostly write at this level, but we're actually going to do a little bit of writing at the level of the ones and zeros. We're going to get some practice actually writing machine code, binary code, based on what we want something to do at an assembly language level. And we'll also spend a little bit of time saying, hey, if I saw this pattern of ones and zeros and I was a CPU, what would I do? So reversing the process of going from machine code back to assembly language. So we'll play those games in some homework assignments. And we won't really worry much about loading and linking. That's really a subject for an operating system course. But this is, if you write a C program and you say, I want to take a square root, well, where does the code for that square root come from? You don't write it yourself. When you compile, you say -lm, link the math library, and machine code for that square root function gets pulled in to your program. That's happening in the linker and the loader stage.
I had that button so many times.
I know, it's so easy to forget, and it's like, it's probably the most common thing that we need to put a -l on, and we forget. Towards the end of the course, we'll spend some time doing some compilation by hand, going from C code into assembly language, because that helps us understand both C code and assembly. But it's a good way to get more practice with assembly language. So we'll kind of be all over this diagram throughout the course. All right, so let's as I think I mentioned up front, this course is a mix of hardware and software, and we'll ping back and forth between them. So let's ping over to the hardware side. So the CPU we're using for this course is made by a company, used to be Microchip, they've been bought. But Microchip, it's a processor called the PIC. PIC is a whole line of processors, and the chip we're using is the PIC 18F1220. That may not mean anything to you now, but you'll be mumbling it in your sleep by the end of the course. 18F1220. It's a microprocessor, but it's actually considered a microcontroller. It's not something that you would put inside a laptop, for example. It's not that kind of processor. If you have a laptop, you probably have an Intel processor inside or an AMD. And those are very complex chips. They are CPUs that understand thousands of instructions and can do all kinds of very complex operations. Their language of ones and zeros is very complex. And the reason... So if you have a laptop, you probably have either an Intel or an AMD CPU inside. And those CPUs are extremely powerful. They understand a very complex machine language, a very complex binary language. They can do all kinds of sophisticated things at the hardware level. And they're very expensive, and they're very big, right? They have perhaps, 1 billion transistors inside. And that's one type of processor. The PIC processor we're using, which somebody posted in chat, 18F1220, is kind of at the other end of a spectrum. It's a very, very simple processor. It has, 30 or 40 instructions to it. Intel processor has thousands of instructions. PIC processor, very few instructions. So there's this general notion of a complex instruction set computer or a reduced instruction set computer. So CISC and RISC. And it's not a rigid line, but complex instruction sets are things like, for example, a Pentium. Reduced instruction sets are things like the PIC processor we're using. If you use an Arduino that has a CPU that's an ATmega 328 usually, that's a reduced instruction set. Most computers, most CPUs on the planet are reduced instruction sets. These complex CPUs, Pentiums, AMDs, things like that, they're less than 1% of the CPUs on the planet right now. They are very popular in laptops and desktops, but that's pretty much it. And a lot of laptops that are starting to pop up, Chromebooks and things like that, are moving to reduced instruction sets. So we're working with a relatively simple CPU, which is good because we're going to learn a lot of details about it. And an equivalent course to this that was based on, say, the Intel Pentium would be probably a significantly more difficult course. Just a lot more to learn and a lot more to sort of grapple with. Why do we have, these processors that are so simple in comparison to, say, an Intel processor? Because a lot of these processors are not used for a desktop computer or a laptop computer. They're used to control your microwaves control panel or to, operate your mouse. There's a little computer inside here that, responds to button clicks, and if I hit this, it changes the resolution and so on. There's a processor inside, right? You don't want to write, a Lab 5 traffic light controller circuit to control a mouse. You want to put a little CPU inside and write some code. But it doesn't have to do, the complex, sophisticated things that your laptop does, for example. So embedded systems, the key fob, if you have a smart door lock, that you can, unlock your car remotely with a remote, a controller inside your refrigerator, all of these things, these are using very simple processors, and a lot of them are PIC processors. So what we're learning in this course, we're learning one particular CPU, but the concepts kind of cut across a lot of different types of systems. So here's the data sheet for the 18F1220, and as I said, it's 308 pages long. And so you don't want to memorize this, and you don't want to print it out, but download it and keep it somewhere handy. It's bookmarked, but we can look at the beginning of this, and it will not be too different from looking at the data sheet for a 7408 quad AND gate or a flip-flop or something like that. So there's the sales pitch in the beginning, the features and the special features and all this kind of stuff. So this kind of gives you an overview of what this device is. And it's a CPU. It's got a 10-bit A to D, that's an analog digital converter, nanowatt technology, so you can use it in low power applications like, that keychain for unlocking the door on your car. You don't want to have to change the batteries in that. Right, so you want a very low power device, so PICs are low power. And there's two versions of this. There's the 18F1220 and the 18F1320. And their only real difference is the amount of memory that you have for your program. And the 1220 has 4,000 bytes of program memory. The 1320 has 8,000 bytes, so twice as much memory. So these microcontrollers are sort of self-contained computers. They have the CPU that does the processing, but they also have memory for storing a program and storing data, and they have the stuff you need to interface with the outside world. So kind of classic block diagram of a computer. So CPU is the central processing unit. That's the brains of the system, right? It performs instructions, it makes decisions, and so on and so forth. The instructions that tell the CPU what to do are stored in a memory. Okay, a bunch of flip-flops if you like. It's a different technology, but you know, picture a bunch of flip-flops put together in an organization so you can store coded instructions, machine code, to say, hey, here's what I want you to do, right? So a list of instructions. And the CPU reads instructions from here and performs operations according to those instructions. And those operations might involve, you know, reading, modifying, and writing data, which could be stored in the memory, or doing some interaction with the outside world. Read a switch. If the switch is closed, turn on this LED. Display the number 7 on this 7-segment display. Send a high and low pulse to the speaker 40,000 times to sound a tone for 5 seconds, right? So all of this is basically contained inside this one chip, and it's an 18-pin chip, and we should be back in person by winter quarter, and you can go in the lab and you can, you know, look in your parts box and actually see these chips and work with them. All right, so 18 pins, right? It looks like a slightly bigger version of an AND gate, but it's got this whole CPU inside that can process instructions and make decisions, modify data, read memory, write memory, and interact with the outside world. All right, so here's the pinout for the 18-pin version. There's a 20-pin version, but here's the pinout for the 18-pin version. We're not really worried about this because we're online this quarter. So we're doing most of our work in simulation. So we don't really need to worry, you know, what pin 1 is versus pin 2. But you put power on here, you put ground on here, and then everything else is just sort of like input and output. They come in tiny little 28-pin packages, quad flat, no lead packages, and so on and so forth. And this is more kind of sales pitch, all the features and reasons why you should be using this. Block diagram. So we'll come back to this throughout the term, and this will make more and more sense. But, you know, this is useful to take a quick look at and think about as we dig further into this device. You know, a lot of this is the CPU, but for example, this is the memory. So this is the 4,000 or 8,000 bytes of program memory, the memory that holds the instructions that tell the CPU what to do. Here's a bunch of circuitry for interacting with the outside world. Here's an ALU. So in 250, we learned about arithmetic logic units. This is a block that can add, subtract, and multiply 8-bit numbers. Here's the multiplier up here. So this mainly adds, subtracts, and does logical operations. But it can do multiplication of 2 8-bit numbers. Here's a special register called WReg. We're going to work a lot with that. And then here's another memory, which is called data RAM, random access memory. This is where the numbers that we want to read and modify and write are stored. So this is an important distinction. There's actually 2 memories in this chip. There's program memory, and then there's data memory. And those are pretty distinct from one another. Now, other CPUs, like an Intel processor, you have one memory. And it's, you know, this DRAM that you buy and you put into your laptop, and it's got, you know, 16 gigabytes of memory, right? But on the PIC processor, these are separate memories, and they're actually physically distinct structures.
I have a question.
Sure.
You can't add memory to this chip.
You cannot.
The program memory is it.
That's it, yeah. So you got 4,000 bytes to play with, which is actually a lot. If your goal is to do something like, you know, control the timer on your coffee pot. If your goal was to make a web browser, probably not enough memory for that, or an operating system, or a fancy game. But you can pack a lot into 4,000 bytes, and we won't come close to using that full capacity in the stuff we do. A few hundred bytes is going to be probably the most that we'll use. All right, so one more piece of computer architecture to talk about. The program memory stores the instructions, right? So how does the CPU know which of these instructions it should be executing? Because we have 4,000 bytes worth of instructions. How does the CPU know what to do? So there's a counter called the program counter. And the program counter basically points to one of these instructions. And wherever the program counter is pointing, the CPU is going to execute the instruction stored there. And usually when it finishes executing an instruction, it increments the program counter to point to the next instruction. And the CPU will execute that, and it will increment the program counter to point to the next instruction. And so the behavior is, starting with the first instruction in the memory, the CPU just executes one instruction after another. And it just goes sequentially from the beginning, with a few exceptions, which is we can do things like jump instructions, branch instructions, which say, hey, don't execute the next instruction, change the program counter to point to this other area of memory, and let's start executing instructions from there. And so there's... Go ahead.
So it's just going to read all of the bytes in the memory sequentially.
Pretty much, yeah. Unless you tell it to read from somewhere else. And we can do that. So that's called a branch instruction or a jump instruction. And so this right here is your program counter. And pretty much everything in the PIC processor is 8 bits. And so this BSR is 8 bits, and this FSR0 is 8 bits, and this WREG is 8 bits. PCL, PCH, PCU, those are 8 bits each. But we put those together and we get, a 24-bit program counter. Because 8 bits gets you 256 things. Well, if we've got 4,000 bytes of instruction memory, we need more than 8 bits in our program counter. So there's a collection of registers that act as our program counter. And, this basically gets incremented after each instruction unless something else happens that says, hey, let's load a new value into here. So that's our sort of general flow. All right, so go ahead and send me an attendance note. Let me know if you're here, and let's take a 5-minute break. And then we'll come back and we'll start digging into some more details of how we instruct this processor on what to do. So send me an attendance note, and we'll come back in 5 minutes. We're at 4 minutes, 18 seconds. All right, we're back. So also on Canvas, I posted a list of pages from the data sheet that I find particularly useful. So, you know, the data sheet's 300 pages long. I've got about 18 pages from there that I seem to go back to again and again while working on material in this course. So I'll often use this, and if you want to print something out so you don't have to look everything up online, that's a suggestion for pages you might find useful, or you might want to you know, come up with your own subset of the data sheet that's relevant for you. But you know, because you probably don't need the pinout since we're online. But block diagram, and then a description of how instructions get coded. And we're not gonna plow through this today, but we'll come back to this on Thursday probably. But this is basically how the ones and zeros get written to tell the CPU what to do. And there's different types of instructions that we're going to look at next. But depending on the type of instructions, you code this information in different ways in binary. So for example, these are assembly language instructions. These are the human readable, human writable ways of telling the CPU to do something. And this gets converted into 16 ones and zeros. And those 16 ones and zeros, that's what the CPU's hardware can actually read and process and respond to. And so this is really the key to converting between assembly language and machine language. And so this is the format for instructions, and here we see the specific codings used for each instruction. So for example, there's an instruction called INCF, increment a file register. And it gets coded as this collection of 16 bits. So when we start working on converting, you know, between machine code and assembly language, this will be a useful table. So table 20-1, and it's also a useful place to go and see a quick description, a quick synopsis of all the available instructions you have. So, and this is the full set of every instruction we have on the PIC processor. So it's these so-called byte-oriented instructions, things that basically read, modify, write memory, a few instructions for working with bits, which we'll talk about more. The control instructions that say don't change the PC to be the next instruction, change it to be something else. So that's what these instructions do. And then a few oddball instructions, something called literals, and then these, which we won't talk about much, and that's it. So I mean, it's a pretty short list of instructions. And then some other information that we'll get to later on in the course about addressing status register and so on. So like I say, probably a good strategy is work with the data sheet and just sort of make notes for yourself which pages you use the most, and then at some point just print those off into their own PDF file maybe. Is there a question? Okay.
I had one
Yeah.
curiosity.
Mm-hmm.
Is there a C compiler for this processor?
There is. There's a few of them actually. There's a free one which is very poor quality, but it works well, just to convert C to PIC. And then there's ones you can pay for that do a better job, that are more efficient, and so on. But yeah, you can get C compilers for this. You can download them from Microchip's website. All right, so assembly language. So, you know, most of our instructions are either saying, you know, grab something from the data memory, do something to it, write something to data memory, right? Those are the byte-oriented instructions, or do something with some sort of I/O, right? Read from a switch or write to an LED or something like that, which are also mostly byte-oriented instructions, but setting up this system, right? Or, you know, change the program counter so that instead of reading this instruction next, we're going to jump down and read that instruction. Or we're going to test some condition. We're going to say, is this variable different from 0? And if it is, come down and do this instruction. Otherwise, do the next instruction. So we have these different kinds of instructions to write. But most of these break down into two pieces. There's an opcode and an operand. And an opcode is basically like a verb, and an operand is basically a noun, actually like a direct object. But this is an action. This is do something, add, subtract, increment, exclusive or, jump, test. This is the thing that we're doing that action to or on. So increment this variable. Compare 0 to that variable. And so most of our instructions, if we write them in assembly language, they're going to have two pieces to them. The first piece, which is an action that we want to have performed, which we call an opcode. And then a second piece, usually, which is called an operand, which is the thing that the action is being applied to. And so let's go to the full data sheet. Actually, let me switch this over. And if we come down to chapter 20, so chapter 20 is the instruction set summary. So this goes through all of the instructions available in the processor. Let's just pick one. Let's look at increment file register. Increment F. So the way this instruction works, I would write something like increment file register X. And increment means add 1. So I could put a comment. So my comments begin with a semicolon. And my comment might be, you know, x equals x plus 1. That's a horrible comment, but I'm putting it in for the sake of explaining this. So this is an assembly language instruction whose purpose is to take the value of this variable x and add 1 to it. All right, so what is this variable x? It's what we call a file register. And it's part of this data memory. It's part of this chunk of memory locations that we have where we can store information that we want to process. And our data memory is pretty small. We basically have 256 bytes of variables. Our program memory, remember, we have 4 kilobytes. Data memory is even smaller, 256 bytes. That's it. So this X is referring to one of those 256 locations. And, you know, in C, we can just say something like integer X. And that will tell the compiler, hey, X should be an integer, and it will work with the other pieces of this tool chain and figure out where in memory that variable X should be stored. For us, we've got to tell the tools where we want X to be stored. We're going to choose one of these memory locations, and we're going to say, I'm going to put variable X like right here. I'm going to put it at location hex 80. And so part of the program we write would say, I'm going to store a variable called X at data memory location hex 80. And then when we say increment file register X, that will get converted into ones and zeros that say, hey, read this byte from data memory, add 1 to it, write it back. So we are really, really down at the metal level here, right? We are scraping the surface of the actual hardware. higher level languages, right, we can just kind of like hang out and type programs and compile them and not really worry about what's happening down at the CPU level. With assembly language, we're very much involved with the actual hardware level. And so that takes some getting used to. But honestly, it's also what makes it fun to work in assembly language, because you have complete control over, you know, the whole system from the lowest level hardware all the way up through the high level behavior. All right, so this is an example of an assembly language instruction. And this would get translated into some pattern of ones and zeros. So the 16-bit pattern corresponding to increment file register X, for example, would be a 0010 followed by a 10, and then two other bits labeled D and A, which we have to talk about, and then 8 bits labeled F. Okay, these 8 bits specify which of those 256 data registers you want to increment. So if I said I was going to increment file register 80 hex, this would be the bit pattern corresponding to 80 hex. And then D, if I... Yeah, question?
So that 8Fs would be like the end of the data memory, right? That's the address, right?
Yeah, so if, for example, let's say my file register was hex 80, right? If I write hex 80 as an 8-bit number, that looks like this. So that would be the 8Fs that would be used in place of this. So this is not hex FFFF. This is just saying there's 8 bits of information here that correspond to the thing that you're trying to increment. So if I was trying to increment file register 80 hex, then those Fs would be 10000000. And when we work on actually converting between assembly language and machine code, we'll see more examples of this. And it will probably make more sense. All right, so for the increment instruction, this tells us, you know, the syntax is increment file incf followed by the name of the thing you want to increment. The thing you want to increment should be between 0 and 255 because it's specifying one of those data registers. DNA or 0 or 1, and those have special meanings we'll talk about. The operation is to read the contents of that file register, so parentheses F means read the contents of that data register, add 1 to it, and then store it somewhere. Store it in some destination. Now, where are we going to store it? Well, there's actually 2 possibilities. I could say increment file register X and store it back in X. In other words, I want the destination to be the same as the thing that I incremented. So in that case, I want my value of D here, this 7th bit, I want that to be a 1. If D is 1, the result is placed back in file register F. So if I coded this as a 101, that 1 right here where it says D tells me increment X and store the results back in X. And I'm not going to worry about the A bit yet. Yeah?
So the first 4 bits are the operation.
Mm-hmm.
The next 4 bits are where the where the destination should be, and then the next 8 bits are the address.
Pretty much. So actually the first 6 bits here are the opcode, the operation 001010. This single bit D, the 7th bit, is either a 0 or a 1 and says where should we write the result to. And if we make that a 1, the result will go back into X in this case, right, the file register. And then these 8 bits, yes, you're exactly right, that specify what it is that we want to increment, which file register. So these are just templates, right? If I wanted to assemble an instruction like increment file register 80, this tells me what 1s and 0s I should end up with. And so there's a description here of what it does. We don't have to worry about words and cycles, but this is how much space it takes to store this instruction. This is how long it takes to execute this instruction. And then there's some examples. If we have this register count that's equal to FF and we say increment, then after incrementing, count will be equal to 0, 0. Because FF is 255. If you add one more, you get 256. But you can't store 256 in 8 bits. It rolls over to 0. Right, just like our 4-bit counters in Engineering 250. So every instruction is specified like this. And, you know, here's a decrement file register instruction. It looks exactly the same, except it takes the contents of file register F, subtracts 1, and stores that in the destination. And the opcode is different. It's 0, 0, 0, 0, 0, 1, and then a bit for D, a bit for A, and then 8 bits for F. So we're mostly going to write programs using things like decrement file register, things that look like this. Decrement file register count. Or go to some location, go to there. Increment file register count. Do an inclusive OR. All right. So for our first lab, we don't really need to understand assembly language. Right? The first lab, you're given the assembly language, and the whole purpose of Lab 1 is to get familiar with the tools that we're going to use in working with the PIC processor. So let me start talking about Lab 1, because I want to make sure we have time to get through all of that. So Lab 1 is kind of a hello world for using the tool set. And the main software we're using for this course is something called MPLAB X. And it's an IDE, it's an integrated development environment, so it has, you know, the ability for us to write programs, to assemble programs, to check their syntax, and to simulate those programs. And then if we had physical hardware, it also has the ability to change those programs into a form that we can push into this PIC processor chip that we can actually load into the program memory of the chip. And normally, you know, we have to have a special device called a programmer, and we hook some pins of that up to the physical PIC chip, and we hook the programmer up to our laptop with a USB cable. And then in this MPLAB tool, we hit a button which says program the device, and it shoves the bits into the program memory of the PIC. And then once we've done that, we have a little 18-pin chip, which every time we put power on it, will start running our program. And we can take it away and come back 20 years later and put power on it, and it'll still run our program. So it's a non-volatile memory. We're not going to get to that part of it because we're not in the physical lab. So we're going to go as far as doing simulation. And I have some widget that I've written a couple of years ago to pretend that to do some simulation of a PIC processor that gives us a visual simulation, and we may play with that towards the end of the course. But mostly we'll be working with the simulator inside MPLAB. So let's take a look at Lab 1. I just did something really bad. That was weird. Alright, so Lab 1 is an introduction to MPLAB. So, first thing you're going to want to do is download and install the software. And I'm going to ask you to take about 5 minutes to do that right now, but let me show you how we get started on that. So, you need to use version 5.1. If you use a newer version, they've disabled some of the features that we want to use. So, click through on that link. And we're looking for MPLAB X, and this should work under Windows, Mac OS, or Linux. But we need version 5.1, so you need to come down here, and that version is currently on page 7, so just click on 5 and then click on 7, and down here MPLAB X version 5.1. Download that for whichever version of your operating system you have, and then go ahead and install it. And let's take about 5 minutes and go ahead and do that.
What if he got
5.1.
What if he got 5.5?
Nope. Get rid of that and go back to 5.1.
Okay.
I don't know where things started to break, but 5.1 was the last one I knew of that worked. Worked for what we need to do.
I'm sorry, could you repeat one more time which software?
5.1.
Okay, thank you.
It's in the lab report, the lab write-up. And the link is in here also.
Okay, I'm clicking on the 5.1, but unfortunately it's not opening anything.
Try right-clicking and saying Save As.
Save Lucas. Yeah, it's having issues. It's saying it cannot be downloaded safely.
It's okay, just tell it to do it anyway.
Save link.
It doesn't like downloading executables usually, but
Okay, I keep on trying to put this thing into a file, but it just will not download it at all. It's saying it just EX can't be downloaded securely, and it's refusing.
what's your operating system?
Windows.
So when I did that, what are you using, Chrome?
I am using Chrome. Should I use like Firefox instead?
No, so let me show you what I'm getting when I try it. So if I say right click and save link as, it'll say can't be downloaded securely. If I click on this, it gives me an option to keep.
Oh, okay.
They make it hard.
They really do.
Yeah.
I'm not seeing version 5.1 at all on here. I used Control F and.
Did you go to page 7?
Try to. You have to like.
yeah.
click on 7.
Yeah.
And
And then if you run it, you should get something like this setup window. And I'm running this under an emulator, so I don't know how well it'll work for me. But let's find out. So I'm going to accept the agreement. And mostly you're just going to take defaults. I would use the default installation directory. And I would just leave all of this. And now ready to install. Go ahead and say next. So I think you can just click through defaults across the board.
I have a question.
Yeah.
I'm clicking on it, but like literally nothing's happening.
What are you clicking on?
It says MPLAB X V5.1.
So right click and say save as.
I'll save as. Okay.
Yeah.
Let's see.
It seems not to work on Firefox. I have to use Chrome.
Okay.
The same thing is happening to me on Firefox.
Interesting.
It'll take me a minute to download it because
That's fine.
it's slow.
Yeah, it's a pretty hefty download.
I already had 5.5 up, but I gotta use 5.10.
Yeah. Firefox, for me, it looks like save as also works. It actually seems to work better. It doesn't complain about it being unsafe. But whatever gets you there.
No, I had a quick question for you, if
Sure.
you don't mind.
Yeah, we got time.
So, I already downloaded it last night before class.
Okay.
And there was some additional stuff at the end that looked like it was optional libraries. Did I need to install any of that stuff?
I suspect not.
Alright, just making sure.
But I'll see if I can get through it here. Like I say, I'm running on an emulator, but I'll see if I can get through it here and see what it says at the end.
Yeah.
Yeah, so for me it's saying it can't be downloaded securely.
Yeah, there's a little arrow or caret next to that you can click on, which gives you a menu that it has an option for keeping it.
Okay. Oh, there you go. It's working now.
Okay,
Thank
cool.
you.
Yeah. And if you can send me a direct message letting me know once you've got this installed, that would be helpful. And if you don't get this installed right now, that's okay, but I want to make sure everybody's like at least started and on the path to it, because you need to have this software working for your first lab. Ready to go, awesome. I've probably got the slowest system of anybody here. Oh, Opera, nice.
It works on Edge for me too, by the way.
Oh, good. Okay,
It works to
cool.
Try that.
Awesome. All right, so I've got a final window here. And yeah, I think you can uncheck all of these.
Yeah, that's what I was talking about.
'Cause
I
I-
just went ahead and unchecked all those.
Yeah, because I think they just bring you to more pop-ups with more options to follow. But I don't think we need any of these. So you can uncheck the things on that last setup box. And that
Okay, thank you,
should,
just making sure.
yeah. Yeah, it's pretty pokey. So, but hopefully everybody has at least got this download started. 6 minutes, okay. Cool. So let's let that keep running if it's downloading, and let's dig into details here. All right, so I'm going to run my version of this for Linux. So once you start running the software, you get a window like this. So this is your integrated development environment. So it's got the sales page up here. You can close out this window if you want. And so Lab 1 is really just kind of following step-by-step instructions to start download and install MPLAB, start it up, put in some code, assemble it, and then simulate it. So you pretty much just follow the step-by-step. So create a project, start MPLAB, file, new project. What I will tell you about this is you want to follow this precisely. And if you misstep somewhere along the way, I strongly recommend close everything out, right? Close the project, go back and start from the beginning. Because you can end up down a bad path. Or at the very least, if you make a misstep somewhere, or if things don't work the way that they're supposed to be working, close out your project, start over again, right? Because it's very specific, and there's things that sound almost the same, but will take you somewhere very different. It's not as quirky as the LDEC tool was in 250, and it doesn't tend to crash and things like that. But follow this as closely as possible. So file, new project, and go through these steps, and then add a source file. And here's the program you're going to put in, and I've put a copy of this in plain text available on Canvas because copying and pasting from a PDF doesn't always work well. So I put this in a text file on Canvas, and then assemble, and you're going to simulate. So let me show you some of these steps in a different example, but this is similar to what you'll be doing. Without going through your lab. So I've got my MPLAB window, so I'm going to say File, I'm going to say New Project. All right, and I'm going to leave this Microchip Embedded Standalone Project. So take the defaults there. And then under Device, I'm going to want to say Pick 18F1220. Now you can find this through the drop-down box, but it's a long and twisting path. So it's easier to just go in here and just type pick 18F1220. If you can type. My CPU is bogging right now. Alright, so pick 18F1220. And then in this next window for hardware tools, you want to click Simulator. And sorry, I can't make this a little bigger. Pick Simulator and go on to Next. And then under Select Compiler, you want MPASM. Don't go with C. Okay, do MPASM. and go on to next. And then project location, you should set this up to whatever location makes sense for you, right? I suggest picking an area that you back up regularly, and that is separate from other stuff. Because when you create a project, it's going to create a whole bunch of files associated with it. So set this up, and you only really have to set this up once, the project location, and then you want a project name. Everything that you do in this course should be its own project. If you're doing a homework set and you've got to write 5 pieces of code, you're going to want a separate project for each one. Don't try to combine more than one program in a single project. It will burn you. You'll end up at some point making lots of changes to your program that don't seem to fix your bug because you're actually running a different program from what you think. So every project, every piece of a lab, every piece of a homework, put it in a separate project. Okay, so I'm just going to call this, you know, Demo 101. And I'm going to say Finish. Alright, and I've got a whole bunch of stuff that just popped up over here. And so I'm going to go to Source File, I'm going to right click, and I'm going to say New, I'm going to say New Assembly File.asm. And then you can pick a name for it. You can call this whatever you want. I'm just going to call it main. And I'm going to leave everything else default. And now I've got a window that I can type code into. So what you're going to want to do is take this code and put it in, starting from here. And like I said, on Canvas, I put a link to the plain text version of this if you can't copy and paste directly. But I'm not going to do that because that's your lab. So I'm just going to put in some kind of random code.
What's the indenting like for this assembly, by the way?
Anything that starts in column 1 is significant. So if you have labels, they start in column 1. Anything that's not going to be a label should start from column 2 or greater. And indenting is pretty much dealer's choice. So if you look at the lab, you'll see a pretty consistent indenting style. Things like number sign, define, or loop start in column 1. Everything else is indented a little bit. These are the opcodes. And then the operands, Izad wrote this code, so he lined up all his operands so you can use tabs to move to a tab stop. And then he lined up most of his comments over here. But spacing is pretty much up to you. And you can find a style that works for you and that, you know, is easy for you to read and makes sense to you. But figure out, you know, how you're going to do it and do it consistently. It will help you. Because after, you know, a few hundred lines of stuff that looks like this, things get really confusing quickly.
I have a small question.
Sure.
Would you say, is this like closer to like C programming or Verilog? Because I know Verilog is like showing the general idea of how something is supposed to function, and C is like giving specific like code. I don't know.
Sure. No, I know what you mean. So this is very much in the style of a C program in the sense that it's an algorithm. It's a series of steps. Do this, do this, do this. Nothing at all like Verilog. The difference from C is just that it's much lower level. These instructions do very, very simple things. But yeah, it's a procedural language, definitely.
Okay, cool.
So I've written a very, very short assembly language program here. org0 is just, and we're going to go over this more, you know, starting Thursday, but for what it's worth. org0 is saying I want my program that I'm writing here to begin at location 0 in the data memory. So in other words, the first instruction I write is the first instruction that the CPU would run. And this is basically saying load a 16 into a magic register called W. This is saying copy W register into file register 80. So this is putting the number 16 into one of those data registers. And then decrement file register 80, and if the result of decrementing is not 0, go back up to where it says loop and repeat. So this will decrement the contents of file register 80 from 16 to 15 to 14 all the way down until it gets to 0, and then it will just sit here and it will just branch to itself. And as I've said, for Lab 1, you don't need to understand what the code is supposed to be doing. You don't need to understand the assembly language. So this would be, like the code that you copied and pasted from the lab assignment. So after you've done this, I'm going to hit the little hammer symbol here to say build. And if I get any errors, so move L is not a valid instruction, move LW is. So I'm going to change that and hit the hammer instruction. And let's see. This is what you get when you play without a net. Oh yeah, and there should be an end statement at the very end. So some general things on assembly language, right? Most of the spacing is irrelevant, other than some things have to start in column 1 and other things cannot begin in column 1. Uppercase, lowercase is sometimes critical, sometimes not. It's critical for operands. It's not critical for opcodes. So I could do lower.
Do you always have to do it for loop there?
Say again?
Do you always have to capitalize the L in loop? Is like that a spot?
If I had my label called loop, I'd have to use the same uppercase, loop down here. But I could call my label lowercase loop, and I could say go to lowercase loop. So it's like variables in C. You can use uppercase, lowercase, however you like, but it's significant, right? If I call this lowercase loop and I say go to uppercase loop, it'll complain that it doesn't know anything about uppercase loop. But I can choose to call it whatever I want. Some of these things like port A, port B, those have to be uppercase, but we'll get through those when we actually start learning what these instructions do.
So, I have a question.
Mm-hmm.
So, when you declare loop there and that block of code beneath, that's almost like declaring a function.
Very possibly, but it's really not that sophisticated. When it gets turned into ones and zeros, loop is really just this location in my program. Now, if I wanted to write a function, it would look like this. I would have loop, and then the name of my function. Then I would have the code for my function. And then if I made a call to my function loop, it would jump down here and start executing that. But it could be other things as well. But yeah, that is how we would make a function. But it's not necessarily a function. But yeah, same idea.
So it's basically just go to this block of code here defined under loop.
It's really go to this instruction. When I say go to loop, it says this is the next instruction you want to execute. And then the instruction after it, and the instruction after it, and so on. And just keep executing sequentially, and unless you find another go to, or jump, or branch. In which case, go off and execute those instructions. So it's really just, instead of doing the next instruction, go and do this other instruction.
What happens if you get to the end of the loop? Does it go back to the line you were previously on when you call the loop?
No. It has no notion that you went here with a go-to as opposed to just falling through. It's very sort of uninspired the way the CPU executes instructions. So if it executes the last instruction of your program and it doesn't say go somewhere, it's going to execute whatever the next instruction is in memory, even if you didn't put an instruction in there. Whatever happened to be there that was left over, that's the next thing that'll get executed. And these are really good things to be thinking about while you're doing this, right? the more you can kind of think about how does this relate to what's going on in the hardware, the more this will start to make sense. All right, so we need an end statement at the end. And the end is just saying there should not be anything else after this. This is back to the days, you know, when you might have your program on a strip of paper that you load into the machine, and what happens if the paper got torn off and the end of your program was missing? Well, if the assembler doesn't see the word end, it knows that part of your program's missing. So when I tried to do this without an end, it gave me a message. I expected the word end. So now if I put the word end in here and I build, now it's all happy. It says build successful. All right, so I can run this, and I want to run it in debug mode. So there's a little button here which says debug main project, or you can come under debug and say debug main project, and it will run. And you know, I've got the little Cylon eye down here scanning back and forth. It tells me my program is running, and it even says here use your program running. And I also had a window pop up. But this isn't very exciting, right? My CPU is running, and presumably it's down here where it's just branching to itself. Not very interesting. So I'm going to hit the stop button, and I'm going to make what's called a breakpoint. So, you know, the simulator, normally it just starts off with the first instruction, it executes the next instruction, and so on. But I can tell the simulator, when you get to this instruction, stop. And come back and let me do my thing. So if I just click over here, this line turns red, and there's a little red square here. That's a breakpoint. And so now if I say go ahead and run my program, alright, so I'm getting an error message here. So this may or may not be an issue. And I think I put this in Canvas. Let me see. So I need to do one extra step, and Izad tried this yesterday, and he did not have to do this extra step. So if you're not getting an error message when you try to set a breakpoint, don't worry about this. But if you're getting this message, try the following. So right-click on your project, come down here under Set Configuration, say Customize, and then down here under MPASM Global Options, check this box that says Build in Absolute Mode. Alright, there's a few little kind of magic things like this. So right-click, Configuration, Customize, come down here under MPASM Global Options, not the one down here, and click this box that says Build in Absolute Mode, and say Apply OK. Like I say, Izad tried this yesterday. He did not have to do this, but for some reason I have to. So I'm going to go ahead and rebuild, and I'm going to run. And now, instead of, you know, saying that it's running down here, it says debugger halted. And it tells me breakpoint hit at line 2, user program stopped. So my simulation of the CPU is frozen right now. It's about to execute this instruction which says move a 16 into this thing we call the W register. All right, so the lab write-up tells you how to do all of these things, right? How to assemble it, how to set up what's called a watch point, and so on and so forth, which will do things like create this window that lets me look at the values of file registers and so on and so forth. So you want to follow the steps of the lab, but just to kind of give you an example of what will happen here, I have a window which is showing me the contents of my file registers. For example, right here at the top, I have file register 80 hex. And its current value is 0 in decimal. It's 8 zeros in binary. It's a byte. And what my assembly language program is saying is put a 16 into this magic thing we call the W register, and then copy the W register to file register 80. So watch what happens. I'm going to hit this button right here, which is a step button. And when I do this, my program counter right now is a 0. And it's about to execute this instruction. So if I hit this button which says step, my program counter changes to a 2. And now this highlighted line, which is in green, which says move W into file register 80, that's the instruction about to be executed. Now my W register, which I can see up here, has a value of 10 hex. My register 80 still has a value of 0, but if I execute this next instruction by saying step, this turns red and it tells me, hey, file register 8 now has a value of 10 hex, 16 decimal, 10,000 binary. So that was the result of this instruction being executed. It moved the number 16 decimal into file register 80. And now I'm about to execute this instruction which says decrement file register 80. So that should subtract 1 from the contents of this file register. Well, right now it's equal to 16. After this instruction executes, it should change to a 15. And sure enough, it became a 15. And it always highlights these variables in red when they change value. So now I'm executing an instruction called a conditional branch. It's saying if the last thing you did not result in a value of 0, go back to wherever loop is and execute that instruction again. So if I step this instruction, it said, oh, 15, that's not 0, it's going to go back. It's getting ready to decrement this register again. And you can see its value is still 15. And if I say go ahead and step, now it changes to 14. So I've got a little loop running here which is doing a countdown for me. It's counting down from 16 to 15 to 14. And if I just keep executing this, it's 13 and 12 and 11. And it will keep looping. So now file register 80 is a 2. If I decrement that again, it'll become a 1. That's still not equal to 0. So it's going to take this branch instruction, go back to line 5, and get ready to execute this decrement. So now when I execute this decrement, file register 80 changes from a 1 to a 0. Well, now this instruction says if the result of decrementing was not 0, go back to loop. Well, since the result was 0, it's not going to do the branch. And so what is it going to do? It's going to fall through and execute the next instruction, which is this branch to done. So if I step it once more, it jumps down here. And you can see our program counter is 8 now, and now it's just going to sit here and it's just going to execute this branch forever. Alright, so we talked a little bit about what these instructions do, but again, we're not really at the point of digging into the details of assembly language programming yet. Okay? We're, for the sake of Lab 1, trying to learn how to use this tool. You're going to do it with this code that's been given to you, and you're going to look for particular locations in memory that you want to watch, and you're going to set up what's called a stimulus, which lets you pretend that you're putting voltages on the pins of the chip, right? And all of this is spelled out in these different steps. So you want to do Lab 1, you want to go through this, put in your code, set up the watch points, set up the stimulus, step through your simulation, hit the fire arrow to change the values of input pins and so on and so forth. And the program will do different things. And what you want to do is you want to observe what the program is doing. And you want to write that up in your lab report. I did this, and then I did these things, and this happened. And then I did this, and I did those things, and this other thing happened. And you want to document basically what you did and what you observed. All right. Now for this one lab, you don't need to write a flow chart because we haven't gone over assembly language yet. Okay, so you don't need to put a flow chart in here. You don't need to put in pseudocode. Okay, but you want to state what it is that you're doing, answer any questions that were asked. You do want a disassembly listing of the code. So let's see if I can do this in fewer than 3 tries. So let me stop my debugger. If I go to Window and debugging output disassembly listing, I get this nice listing of my program that shows me my original code, but also shows it in a standardized representation, and also shows in hex the 1s and 0s corresponding to the machine language of each instruction, and shows where in that program memory each instruction was stored. So at location 0 in the program memory was stored the binary pattern 0E10, which is that 16-bit coding for move LW 0x10, which was what I asked it to do. And down here I said branch if not 0 loop. Well, that's actually the instruction branch if not 0 hex 4, because hex 4 is the address where this instruction at loop is stored. And this branch if not 0 got stored with this 16-bit pattern, and so on. So this disassembly listing is a nice one to put in your lab report. And when you copy and paste this into your PDF, use a fixed space font, right? Courier or some kind of mono font. Change your font so that all this stuff still lines up. And don't be afraid to reduce the font. You can use a 6 or 8 point font. I can zoom it in the PDF, right? Or, you know, worst case, rotate this. Put it in landscape mode instead of portrait.
Can we copy paste this into like a text editor and then put it back into our document?
Yeah.
So it looks better?
Yeah, totally. You can usually just copy it from here and paste it directly into, you know, OpenOffice or Word or whatever, and then just tweak the fonts.
Would taking a screenshot of it or screen cap of it and putting it in work too?
Don't do a screenshot, just because they end up usually not being very legible, and if I want to try running your code, it's harder to grab the code out of there. So yeah, take the actual text file, the actual text from this window, and put that in.
All right.
So starting, sorry.
Mm-hmm.
Starting from number 1, like row 1, or just starting from like the actual code.
I would do the whole thing.
Okay, cool.
So everything that you get when you select, so just Control A to select all. And this will make a lot more sense once we start writing the code ourselves. All right, so yeah, so that's pretty much lab 1. Like I say, it's really kind of a hello world. You're given all the code, you're given all the steps to perform, and it's just going through those steps. And then we'll use what you learn in this lab. You'll use that in all the subsequent labs as you write code and put it in and test it and debug it. You'll want to be able to do things like set up inputs, look at outputs, and so on and so forth, single step, etc. All right, so our class ends at 2. I'm going to switch rooms to that other Zoom link, and I recommend if you don't have a conflict right now time-wise, right, go ahead and start working on lab 1, at least to the point where you can get code entered in and start some of this. I'll be in my office until 4 o'clock, so hop in there and ping me if you got questions about this or about anything else on the course, or you want to talk about logistics or whatever. Otherwise, have a good one, and I will see you on Thursday.
See you on Thursday.
All right, thanks.
Thank you. Yeah.
Have a good day.
Thanks, you too.